All right, good day. This is Professor Grenfell's Math 12 Statistics class, and we are today opening up a new chapter, Chapter 9. We're going to be performing more hypothesis testing, and now in this case, we're going to be able to test two parameters. That is the same parameter from two different populations, and we'll be able to make a comparison. So in this first section, we're going to be assuming that we have the population standard deviation for both of these populations, and thus we get to use the z-test. All right, so there we have it. 9-1 is going to be on testing two means using the z-test. And so here we are in a situation where we wish to make a comparison between two different populations and their, well, in this case, their population average. And so what our hypothesis test is going to be looking like, essentially, in these first two sections, is, on the one hand, we're going to say, well, until you give me any evidence, I cannot assume that there's any distinction between these, right? If I don't know anything about these, I have to just assume that they're the same, okay? And then we're going to be saying, for our alternative hypothesis, we're going to be saying something like this. Mu1 is not equal to mu2. That would give us a two-tailed hypothesis test. I wrote H2 for the second alternative hypothesis. No, just kidding. It should be the other option for H subscript 1 is that the one is less than the other, or you could compare them the other way if that was the way that the problem was presenting itself. Oh, sorry, that is equivalent. So we could say mu subscript 1 is greater than mu subscript 2. Okay. Now, with all of these, this is an okay way of writing it. This might make more sense. But when it comes to computing the test statistic, because of the way that we have to compute this, it's going to be more usable if we write our hypotheses in this way. For H subscript 0, we should, instead of saying mu1 on one side and mu2 on the other side and saying, okay, we hope these are equal, what we can do instead is say this. Let's take the difference between them. We'll just subtract the second one away from the first one. mu2 subtracted away from mu1. And we'll just say, we'll just say that that difference is 0. Okay, so basically, instead of saying our two different quantities, remember, we don't know the population average for either of these. All we are given is a sample, and in this rare instance, we either by assumption or somebody just told us, we have the population standard deviation. But remember, when we're doing a test, we never test the sample. That's what we gather. That's what we know everything about. We make conjectures and we test them about the population. And remember that that's never 100% accurate. There's always the chance that we could be incorrect. So here, our alternative hypothesis, if it's a two-tailed test, we're going to say mu1 minus mu2 is not equal to 0. For a single-tailed test, this would be a left-tailed test. We're going to say like this. Mu1 minus mu2 is less than 0. Okay? So look, if mu1 is less than mu2, then when we take away the larger one, that would be a negative value. Or the third alternative hypothesis would be that the difference mu1 minus mu2 is greater than 0. That would be a right-tailed test. Okay, just a few conditions on our data sets. They have to be random samples. And now here's the important thing. The samples must be independent of one another. That is, there cannot be any relationship between the subjects and the sample. So we'll kind of make sure to mention that when we come across that in an example. And then thing number 3 is that the standard deviation of both populations must be known. And if sample sizes are less than 30, then they must be normally distributed or approximately normally distributed. So let's say we have population 1 and population 2. Oops, forgot how to make an and population 2, sigma 1 and sigma 2 are both known. I'm sorry, I apologize. I said population 1 and population 2 are both known, but that doesn't make any sense. The standard deviation for population 1 and for population 2, those quantities, those population parameters, we're going to assume that we know them. But remember, that actually means that we secretly don't know them, but we're pretending that we do. So this usually is not good practice. In a statistics class like this, we're doing this as introductory material to get us used to the techniques that we're going to have to use in a more real-world situation. So, whoops. The standard deviation for this distribution, the difference in our populations, is going to be the population variance for the first population divided by the sample size for that first population. And then second of all, it's going to be the variance for the second population. Remember, the variance is sigma squared divided by the sample size for that second sample that we're using this. So this is the standard deviation for, that looks like a 6 too much. This is the standard deviation for chi1 bar minus chi2 bar. All right, and so therefore our test statistic, remember we get to use the z-test, so we'll be using the z distribution. It's going to be chi1 bar, oops, minus chi2 bar. And then from that, we're going to take away mu subscript 1 minus mu 2. And then all of that is going to be divided by that, this one, the standard deviation for our distribution of differences. So this is going to be sigma 1 squared over n1 plus sigma 2 squared over n subscript 2. And then that whole thing we're going to take the square root of. So this is our formula to compute our test statistic. And notice here, this is another reason. This is why we want to write our hypotheses written like this, so that this value right here is not a mystery, okay? If we set them equal to one another, then it becomes a little bit too difficult to figure out what it is that we're trying to do. All right, let's do a quick example. All right, so here we are looking at example 9-1 on page 491. And this is pertaining to leisure time, apparently. a study using 2 random samples of 35 people each. So here we have n subscript 1 equals 35 and n subscript 2 is also equal to 35. Found that the average amount of time those in the age group of 26 to 35 years spent per week on leisure activities was 39.6 hours. So this is our second factoid here. Chi-bar subscript 1 is 39.6. And where is it? Oh, I left off. And those in the age group from 46 to 55 years of age spent 35.4 hours. So there's our second sample average. Assume that the population standard deviation for those in the first age group found by previous studies is 6.3 hours. So there is this one, 6.3 hours. And then in the second group, we're assuming it was 5.8 hours. At alpha equals 0.05, can it be concluded that there is a significant difference in the average times each group spends on leisure activities? All right, so there is all of the pertinent information and the question at hand. So let's go through our hypothesis test. All right, so here's step 1. H subscript 0, I've written it as mu subscript 1 minus mu subscript 2 is equal to 0. So that means that let's see, for population 1, we have the age group 26 to 35, their average leisure time, and then population 2 is 46 to 55, their average leisure time per week. We're saying those 2 demographics, there's no difference between the young and the old, I say it like that, and their leisure time per week. So here we have a sketch of our distribution curve, and we've also shaded in the tails of our distribution curve and written down the specified area that's supposed to be underneath those tails. Remember, we take alpha and we divide it by 2, and that's how we got these 0.025 values. And then remember, we find the value that's close as we can get, to 2.5%, and figure out the z value that goes with that. That's how we would do it using the z-table. Remember, we look on the inside of the table and find as close as we can get to this value, and then from there we go out to the end of that row and up to the top of that column, and we read off our critical z subscript alpha. Next thing we'll do, we will compute the test value. Write down the z formula from your own memory. I will pause the video until you have written it down. All right, there is the formula that I got to. The z-score is computed by doing chi-bar 1 minus chi-bar 2. Right, that's our difference in our samples, minus mu subscript 1 minus mu subscript 2. All right, so that is the hypothesized difference in the population means. And then we're dividing this by this whole quantity here, the square root of the entire thing, sigma 1 squared over n subscript 1 plus sigma 2 squared over n subscript 2. All right, so here we are. We have 39.6 minus 35.4, so that is the leisure time hours for the 26 through 35-year-old demographic minus the leisure time hours for the older demographic. And then we have minus 0 here. And remember, This is the reason that I prefer to write it as mu subscript 1 minus mu subscript 2, because in the null hypothesis, we're saying mu subscript 1 minus mu subscript 2, the difference is 0. Okay, so that is exactly where we get this 0 from. Now, once you see that, it'll basically be the same every single time. So, but that's where it's coming from. And then in the denominator we have 6.3 squared over 35 plus 5.8 squared also over 35, because the two random samples had the same number, 35 people in each. And make sure you plug it in correctly, but we'll let the calculator finish this one off. It's 2.90. And then just going back to the sketch, I didn't want to flip the page back, but I'll just recreate it. That was plus or minus 1.96. So there's positive 1.96 and negative 1.96 on the left. Okay, so our test statistic 2.90 is right about here. There's 2.90. So notice it is well inside the critical region, the rejection region. So our decision in 4 is going to be to reject the null hypothesis, H subscript 0. And then, of course, step 5, summarize the results. And so here we say the evidence, always the evidence, right? The evidence shows a significant difference between the leisure time hours of these two groups. That's how we would summarize that. And we'll close here and pick up with the next example in just a moment.